Hey, how's it going, everybody? Today we have an amazing problem for you guys that I'm pretty excited about, right? So the problem's called keys and rooms. So let's quickly go ahead and read the problem statement, guys, right? So it says there are n rooms labeled from 0 to n minus 1, and all of the rooms are locked except for room 0, right? Your goal is to visit all of the rooms. However, you cannot enter a locked room without having its key. Okay. When you visit a room, you may find a set of distinct keys in it, right? So each key has a number on it, denoting which room it unlocks, right? And you can take all of them with you to unlock the other rooms, right? So it says given an array of rooms, right, where rooms of I is a set of keys that you can obtain if you visit room I, right? Return true if you can visit all of the rooms, or false otherwise, right? So very, very good thing they're telling us, guys, right? So interesting. So we get the concept that we're given n amount of rooms, right? Uh, and for each room, there are keys, a distinct set of keys, right? And then we can use those keys to unlock other rooms, right? For example, we have this example, right? We see this is room 0, this is room 1, room 2, and room 3, right? Meaning we have like 4 nodes, right? We have 4 rooms, I mean, right? 4 rooms, right? We have 4 rooms. And for each room, right, we have a set of keys in there. And our goal, right, is to try to use those keys to unlock other rooms, right? So for room 0, we have the key for room 1, right? So therefore we will use that key to open room 1, right? And then we see from room 1, we have the key for room 2, and then we can unlock room 3 as well, right? Room 2, and then we unlock room 2, we see the key for room 3, we visit room 3. There's no keys there, but we're good. We visited all of the rooms, right? And that's where we return true, guys, right? And then for this example, right, we are given same amount of rooms, right? 0, 1, 2, 3, right? 4 rooms. And we see the keys, right? So for room 0, we have the keys to room 1 and 3, right? So we say we visit room 1 first. We have another set of keys, right? We can go back to 0, room 0, but we already have access to room 0, right? So we're good. Let's try room 3. Okay. Okay, room 3 is right there. I go back to, no, I already visited 0, right? I already have the key to 0, so that doesn't help me. So go back to 1. I'm already at 1, so that doesn't work. Therefore, I return false, guy. We can't visit 2 because nobody else has the keys to room 2, right? So that's why we end up with a false, returning false, right? So hopefully you guys have a better understanding of the problem, right? So let's kind of see what do we need to do, guys, to solve this problem, right? Because it's always good first to make sure you understand what the problem is asking you, right? And what's kind of the goal, the point of the problem, right? So you can be motivated to solve it, guys, right? So very important. Okay. So how can we go about it, guys, right? So let's see. So we see we always start with room 0, right? Because the room 0 is the one that's not locked for some reason, okay? Interesting. So that's we can use this to our advantage, right? Okay, so we start from room 0, okay? And then we visit other rooms. Visit. Okay, that's interesting. Uh, Also, almost reminds me of something, right? So let's see what they're talking about. Okay, so we got 1. We can go from 1. When we're at a particular node, we can go from that node to another node. We can go from when we're at a particular room, we can go from the keys available in that room to the other rooms, right? So from room 0, we can go to room 1, right? Okay. So from the looks of it, right now, we could see that we can kind of model this as a graph, guys, right? As a graph for everybody, right? So a graph. So every room represents a graph, right? And the keys in that room represents the relationship that the nodes have with each other, right? So, and it'll be we could say the edges can be direct edges, right? Meaning from a particular room, right? All of the keys that are in there, right? Those are its neighbors and they're directed edges, right? So we can go from that room to whatever keys are available in that room, right? So for this example, we'll see from room 0, right? We see we can visit 1, right? Right, right? But we go to 1, and then from 1 we can go to 2, right? And then from 2, and from 2 we can go to 3, so on and so forth, right? This example shows it better, right? At room 0, right, it has two neighbors, right? Two direct edges, right? From 0 to 1, and then from 0 to 3, right? Meaning that we can go from 0, right, to 1, and we can go from 0 to 3 as well, right? But it doesn't necessarily mean we can go from 1 to 0, right? Right? Direct edges, right? But when we see that at 1, right, we can go to 0, right? From 1 to 0, and from 1 to 3, things like that. So you guys can't get into the relationship that's the main takeaway, that to see the rooms as nodes, right? And for the edges, right, we see that they're direct edges to show the relationship that we can go from this room to the other room, right? And after we do that, we've pretty much done the hard part. And then now, once we modeled everything as a graph, we could easily apply a depth first search or a breadth first search, whatever you want to do to solve this problem, right? We just do a traversal of the graph, right? We see at the end of the traversal, right, if we have visited all the nodes, right? If that's the case, then we can safely say we can visit all the rooms, or we can visit all the nodes. So we return true, guys, right? Which is the answer right there. Right? And if we can't visit all the rooms, the nodes, then we return false, guys, right? So that's kind of the main takeaway, right? So you can see how we build a graph, we apply that relationship with edges, right? And we apply a breadth first search or depth first search, whatever you feel like, and you solve this problem, okay? At the end, right, you could keep track of the nodes visited in some kind of a data structure, right? And then you check at the end of the traversal, have you visited all of the nodes? If you have visited, then you're good, right? So let's quickly go in with the implementation guide, right? So everything will make a lot more sense, and it'll be a lot more clearer, right? So it should be pretty simple. Yeah, guys, we'll be doing the depth first search version, right? So you can use whatever traversal you feel like doing, right? But for this video, we'll be doing depth first search, right? You know, the code is relatively simple. Breadth first search simple as well, right? You just need to. All right, so let's quickly do that real quick. So we're going to have a set, guys, to help us in keeping track the number of nodes that we have visited, right? So that's what we're doing here. Okay. Yep, and then after we do that, guys, we're going to do a depth first search. And then at the end of the depth first search, guys, right, we hope to have, we're going to be checking the amount of rooms that we have, right? Is the amount of rooms that we visit, is it the same as the number of rooms, right? If it is, we're simply going to return true, right? This statement will be true if that's the case, right? This is what I'm doing here. Hopefully it makes sense to you guys, okay? And then what we're gonna do, we're gonna implement our DFS function right now. Void DFS. So DFS function, we're gonna pass in the rooms, right? We're gonna pass in the current node. And we're gonna pass in the set, right, to help us in keeping track of that. Okay. Let's copy this one. That's gonna be important. Put it as a header. Okay. And the current node and the set. All right, we're just gonna copy this here. And yeah, we're gonna do as we visit the nodes, guys, where we're going to simply add it to our set, mark it as visited. And after that, what's next for us to do is to visit our neighbors, okay? And then we have access to our neighbors, the other rooms that we can visit, right? In our list, okay? And then how do we know which nodes to visit, right? We're going to check if that node has not been visited, right? If that neighbor that I want to visit has not been visited yet, then I'll do a DFS on there. Pass on the rooms, pass on the neighbor, and the accepts. Okay. And then my neighbor is gonna visit each neighbor as well, the room that he can visit, right? And then at the end of all of the FS graph, right, the traversal, the set will have the amount of nodes that were visited, and then we just compare with the number of rooms, and then we return that true or false depending on if this is a true statement or not, right? So yeah, this is a very, very nice problem to kind of get us familiar with, uh, be able to model things as graphs, and good exercise for our DFS preferences traversals, right? So very, very good problem, guys, right? Seems that we passed the small test case. Let's press submit. So we passed all the test cases, guys, right? Awesome, guys. We're going to pass all the test cases. Pretty excited about it. So to just do a quick recap, we have a set to help us keep a track of the number of nodes we visited. And then we do a DFS starting from node 0 because that's the only room that's unlocked initially, right? So that's why we start room 0. And then at the end of traversal, we check if the number of nodes visited is the same as the number of rooms that we have, right? If that's true, we return true, right? And then DFS is simple DFS, right? We our set to help us in keeping track of nodes visited, right? So we don't revisit it again, right? And we're like, cycle things like that, right? So uh yeah, we're good. So yeah, guys, I want to thank you guys for taking the time to watch the video, guys. If you guys found value, make sure to give me a like. If you guys are new here, make sure to subscribe because I'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.